Okay, so we're going to talk about induction here. All right, and let me just minimize that, bring that up. This whole thing needs to be over 4. Let me just see if I can use my equation editor for this. There should be 1, but if not, that's kind of okay, I guess. Um, no problem. Yeah, we'll move on without the equation editor. So now here's what I'm going to do. I'm just going to put this whole thing over 4. Like that. Okay. So now here's the thing. For my basis step, they said for all positive integers, I'm just going to show that 1 cubed is equal to this thing over here, right? So T of 1 equals the statement that 1 cubed equals 1 square times 1 plus 1 squared. All right. And then this guy here over 4. Now this would in turn equal 1 times 2 squared over 4. Okay. So now let's take a look at that. It's 1 times 4 over 4. Now, if there were a P of K step, it would look as follows. P of K equals, all right? So that's just the statement P of K. Now we're going to have to show that P of K is true. Well, if this is the statement P of K, then P of K plus 1 would be as follows. All of this up here. But with the following added in. And that's going to be equal to K plus 1 here. This is going to be a plus 1. And there we have that. So now, let's check to see what we have. I'm going to try to write P of K plus 1 in terms of P of K. So here's how I'm going to do that. If this is P of K, then I can also say that this whole thing equals this guy up here, which can be found right here, okay, plus this guy right here. So now I simply have my next term added in. Like that. Okay. So now, as you can see, all I did was add K plus 1 on that side. Now I need to show on the opposite side, however, that all I did was add K plus 1 cubed on the opposite side as well. Okay. So let's take a look at what that will look like. Here I have K plus 1 cubed. I'm sorry, here I have M plus 1. So that's not what I want to write to. Okay, this was P of K. So I need to show that this here plus the other P of plus the K plus 1 are one and the same. All right, so here's what I'm going to do. K plus 1 squared is going to be as follows. It's going to be this guy right here. All right, it's going to be K squared plus 2K plus 1. All right, that's for k plus 1 squared. This guy right here is k plus 1 squared. All right. So in that case, what we are going to have is as follows. Given that we have multiple parentheses, let me just make sure these are well balanced. Okay, great. We have a multiplication of the following. This is k plus 1, and that's plus 1. All right. But we need to have, since this is raised to the exponent of uh, k plus 1, this guy right here, I need to have that there. Okay. That way now you can see that all of the parentheses match. This guy matches this one here. Those two match each other. Those two match each other. This one matches that one right there. Okay. So k plus 1 is going to give us k plus 2. This guy here. And k plus 2 squared. Now, k plus 2 squared would give us k squared um, plus 4k plus 4. All right. So here I have another k squared. To just copy some of this over. And all this is going to be divided by 4. Okay. Now, over here, I had added in k plus 1 cubed. Now, here's what I want to do. Since I'm doing the whole k plus 1, all right, here's my p of k that I had from before. I want to add k plus 1 to that. K plus 1 cubed to that. So now, here goes. This would equal this guy up here plus this right here. Okay. Now, what I'm going to get here is k cubed plus 3k squared plus 3k plus 1. All right. So some of you probably are wondering, like, how did you come up with that? Binomial, uh, the binomial coefficients, basically. Right. So this right here, let me just take that part out. There we go. And let me just see if I can factor out certain things, which would make it a bit better. Okay. So up here, we established that this was true. Okay. But if we can establish that that part there is true, then we should be able to establish something else as well. Let's see. So I'm going to multiply this part out. And what I want to make sure that I am proving is that this will be the case for all integers. All right. So it's supposed to look like this right here. Okay. And let me just make sure that, let's see, I should have everything I need in this particular area. So there will be k's to the fourth over here. If I were to add the k plus 1 cubed over here, remember that we had that 4 over 4 thing? So just going to say the following. I'm going to say that we can combine like terms. All right. It's going to be 4 over 4 times that, which would then give me the following. I'm going to come down here. All right. This is going to be a lot to write, but here we go. I'm going to have this whole thing here. But this time around, it's going to look as follows. I'm going to take this guy, put parentheses there, put parentheses right over here. Because since now they're both over 4, I'm going to divide them both by 4. Like that. Okay, so just make sure these parentheses are all matching. Yes, they do. Okay, great. So now here's what I need to do. I have 4 over here, k plus 1 cubed. And then over here, I'm going to have my other multiplied elements, right? So this evaluates as follows. The first term is going to be k squared times. All right. And I'm just going to put the following here, another k squared plus 2k plus 1. Okay, so that's going to be one group of factors. And then it's going to be 4 and 4 times. It's going to be k cubed plus, let me just take a look. Right over here, I have k cubed plus, I'm going to have also 3k squared. And then I'm also going to have, let's see, 3k. Let's see. Let me just take that back. And to come down here. right? Plus 3k plus 1. Okay, this is going to be like huge and whatnot, but it is what it is. Okay, so now coming all the way down here, once again, rewriting our equation, I'm going to have the following. I'm going to have, starting from this guy, all right, I'm going to have k to the fourth and it's interesting that they left us with such a massive algebraic example, but it is what it is. So I have k to the fourth plus 2k cubed. Plus k squared. All right. And then let me just plus right over here. Now I have to do 4 times all of these, so I'm going to have 4 times k cubed didn't mean to do that as a screenshot. Didn't mean to. My bad. Um, there we go. Then let's see. Then this part here is going to be 12k squared plus 12k plus, let's see, 4. Okay, so now I need to combine like terms here. Okay, so I have k to the fourth, this guy here, plus, here I'm going to have my k cubes collected together. So I'm going to have 6k cubed. Plus, now I'm going to collect my k squares together. So I'm going to have 13k squared. And let me just make sure that that is, let's see. Yes, that is what it should be. All right. So here I have k squared. Over here I have a 12k squared. So that's 13k squared. plus, let's see, my ordinary k's are 12k plus, 1 second. This left me with no single k's, apparently. So 12k plus 4. Okay. Let's see. And now all this will be over 4. Or will it be? I should have supposed to be over 4. Over 4. Yikes, I missed the 4 for this part here. So let me just get that part straight. This should be over 4. Okay. Um, which means that these guys should be over 4. This whole thing over here. Right, so this should be over 4. All right. Now let's see. This guy here should be over 4. And we want to make sure that that is the same as this one right over here. So now here's the question. Is it the same as this one right over here? Well, we're about to find out. Okay, so we're going to take this guy here. All right, that's one of them. I'm just going to highlight him in yellow. Okay, and then the other time we did the k plus 1, it was this guy right here. Okay, and we evaluated that out to this here. So let's show that these are equal now. So this guy up here, when we fully evaluate him, is going to be equal to the following. I'm just going to put a script right next to him. So this is, let's just say that this guy here is equation 2. Because clearly this is becoming very large. And we'll call this guy equation 1. Just like that. Okay. And now coming down here, I'm going to take equation 1, and I'm going to evaluate what equation 1 comes out to. Let me just get this highlight thing out of here. There we go. Okay, so with this guy up here, we have the following. K squared and k squared is going to give me k to the 4th, just like what we have over here. Okay, now the next thing we have is k squared plus 4k, or k squared times 4k. Okay, so k squared times 4k will give me 4k squared. And then we have k squared times, uh, oops, okay, let me just change this to 4k cubed. I'm sorry about that. K squared times 4k is not 4k squared, it's 4k cubed. There we go. Now, k squared times 4 is 4k squared. Then, let's see. That part is finished, okay? So now we're gonna move on to the 2k times the rest of these guys here. So now 2k times 2k, I'm sorry, 2k times k squared will give me 2k cubed. All right. 2k times the 4k will give me 8k squared. Okay. Now, next thing we know, we have 2k times 4. So that's going to give me 8k. Everybody's watching that. So 2k times the 4 gives me 8k. All right. And now we have 1 times this entire second equation. So I could just copy it over because we're multiplying by 1. There we are. Now to combine like terms. All of this is going to be over 4, by the way. But now to combine like terms, this whole thing equals. We have k to the 4th plus, all right, I have 4k cubed plus, let's see, 2k cubed. So this is going to give me 6k cubed. Looking like this guy up here. Okay, plus, next part we have the squares. So 4k squared and 8k squared, and k squared. Say that, 4k squared, 8k squared, sorry, and k squared. That's going to give me 13k squared. Now the next part is my ordinary k's. So scrolling over here, I see that I have just 8K right there and 4K right here. That's going to give me 12K. And now for the regular constants, scrolling, all I have is the number 4. Now I'm going to put those in parentheses. And remember that we are dividing by 4. So let's see. This guy here, equation 1, when expanded, was equal to equation 2, k to the 4th, 6k cubed, 13k squared, 12k plus 4 over 4. All right, so now, here we go. It turns out that P of k of 1 is true. The equality did hold when it came to both of the expansions. So this guy plus the k plus 1 that we did, which is found right over here. You took this and substituted k plus 1, right? Over here, we then, found our polynomial. But then we also did the part where we took the k squared, k plus 1 over 4, and then added k plus 1 cubed to it, and then got this guy right here, okay? And then we multiplied that out, and then went on to get our next equation. This guy right here, which then became this guy right here. And then he turned into this guy over here, equation 2. Okay, so now here we see the whole thing checking out. I know it's hard to like follow a bit, but we can say that P of k plus 1 is true. Okay, so now here's the thing. Now we could say that because we know that this whole principle holds from P of 1 to P of k to P of k plus 1, that P of n is true. It's true for all P of n. All right, just like that. Okay, so you see the equation actually held, and that is the actual result of our summation. Okay, and I'll just put here by induction. So we use induction a lot to be able to draw conclusions over larger cases, even if, we're trying to prove something that's potentially infinite, which this right here is, it's for all n, where n is a positive integer, right? So for P of n is true for all, I'm sorry, I should not have put P of n. I should have put in the following for all n. And where's my epsilon? I'm going to insert a special character, the set theory. Let me just look at my mathematical symbols. There we go. And I just need to find the one for set theory, the one where I say it belongs. Um, so I'm just gonna have to go with the closest looking character, and that character would be, I have to go back to the Greek epsilon, backwards epsilon. No, no. Okay, I'll have to say the following then. I'll do it a bit differently. I'll just say belonging to Z plus or greater than, for all n greater than 0. Okay, I think that's how I have to leave that. For all n greater than 0, and n is a positive integer. All n that are positive integers. There we go. Z plus. I believe that ends it. Okay, questions. Let me just see if there are
I just
any
wanted to
questions.
say thank you. This brought back um, doing polynomials back in high school and
Hmm.
getting to look at all of your work and reading through it and understanding, oh, wait, this is just polynomials in one way or another really helped
Hmm.
out with my understanding. So I just wanted to thank you, Professor.
No problem. I'm glad to help. So, I mean, that's informing is one thing, helping is even better, you know? And I think that students should be helped as much as possible. So, yeah, this is what it is. Don't forget, you also have office hours at your disposal. Um, Now, if we take a look at what they were doing here, you know, this is also another one that's possible. I think this one here might have been a bit easier if we did that one together. Um, let's see, 1 times 2 plus 2 times 3. This one could have been a bit tricky, but I think that's also somewhat possible. Just went with the first one. And, that's the case there. Um, so yeah, that's basically what we have here. And yeah, we work with a lot of polynomials, especially since we talk about, computational complexity. You're going to see that a lot. You're going to see, certain exponents, but it's really just, a sandbox of mathematical expressions and the reasoning on them. So when we talked about the recurrence relations, it's largely the same thing, right? It's a sandbox in which we have familiar expressions. Let's see, 108. Right? And those familiar expressions, it's just a matter of us being able to, balance out the different components in the equations. So in computer science, we use like n and m a lot, and we don't use x's as much, like as in, your mathematical algebra classes, but the same relations still hold, right? And that's important for us all to remember. Any questions thus far? Okay. So we were talking about the cost of the tree up here, okay, and the actual work being done going across, each of these different items. Now, when you see this dot, dot, dot thing, this is just like, when you see the dot, dot, dot plus n in induction. So we're really saying that eventually we lead here no matter how large this tree is. We don't know how many levels it is, but eventually we get here. What we do know is that no matter how large this thing is, as n is larger, which means that we will be, branching further down, ultimately the height of this tree will be log base 4 of n, right? And that's because you have these additional divisions of 4 on every step. So that's where you get the log base 4 of n rather than n divided by some other power of 4. Let's see. So now coming down here with the divide and conquer part, we got as far as saying this part about, the subproblem size for a node at depth I is n over 4 to the I. Thus, the subproblem size hit n equals 1 when n over 4 to the I equals 1, or equivalently when I equals log base 4 to the n, right? So 4 to the log base 4 of n would really just give us n over n because, the exponent and the log base 4 would start to cancel out then. Let's see. So now, um, so next we would determine the cost at each level of the tree. Each level has 3 times more nodes than the level above. And so the number of nodes at depth I is 3 to the I. Okay, let's take a look. At depth I, this is depth 0, so 3 to the 0 is 1 node. But here you have depth 1, so you have 3 nodes. 3 to the I, 3 to the first. 3 to the second here means we have 9 nodes. But now going all the way down, remember we had log base 4 of n. So coming down here, we're going to have 3 to the log base 4 of n nodes, right? So let's just take a look. I'm sure that we're getting at that. Because the subproblem size reduced by a vector of 4 for each level, we go down from the root. Each node at depth I for I equals 0 to log base 4 of n minus 1 has a cost of c of n over 4 to the I squared. Multiplying, we see that the total cost over all nodes at depth I for this whole thing up to, the depth of log base 4 of n minus I is 3 to the I times c of n over 4 to the I squared, which then would equal 3 over 16 to the I times c n squared. The bottom level at depth log base 4 of n has 3 to the log base 4 of n equals n to the log base 4 of 3 nodes. Okay, so 3 to the log base 4 of n And then they said n to the log base 4 of 3. I know you're probably wondering, like, how did they do that? Um, each contributing a cost of t of 1 for a total of n to the log base 4 of 3 times t of 1, which is theta of n to the log base 4 of 3, since we assume that t of 1 is a constant. Now, if we add the cost up over all levels, all right, you have cn squared plus this guy here and the others, all right? And so using the summation of it all, right, you're going to have this particular um, outcome. Now, moving further down, here's what we're just going to say. You see, since the n squared is the largest term on the left-hand side, and here you have n to the log base 4 of 3. If it were n to the log base 3 of 3, it would be 1. But we're talking about log base 4 of 3, right? So that's going to make it even smaller. So the largest term here is the n squared term. So coming all the way down here, you're going to see that it's an O of n squared. So that is a guess for the running time. But now, if this thing is bounded from above by the constant 16 over 13, take a look right here. 1 minus this right here. That would be 16 over 16 minus 3 over 16, which would be 13 over 16. 1 over 13 over 16 would be 16 over 13 because it's inverted, all right? So this constant of 16 over 13, C, right, that's going to be our boundary. Since the root's contribution total cost is Cn squared, the root contributes a constant fraction of the total cost. In other words, the cost of root dominates the total cost of the tree. Now, when it comes to this whole thing here, I don't intend to have you trying to work on things that are way too difficult in trying to figure these things out. If we had to try something like use a recursion tree to determine a good asymptotic upper bound on the recurrence of 3t n over 2 plus n, use the substitution method to verify your answer. Some of these would be a bit easier. A recursion tree, let's see, substitution methods. They verify your bound by the substitution method. So let's just take a closer look at the substitution method. And after that, we'll just call it, you know, a, a day, I suppose. So now the substitution method does the following. Basically, it's just algebraic largely. The substitution method for solving recurrence comprises of two steps. The first is to guess the form of the solution, and the second is to use mathematical induction to find the constant and show the solution works. So we substitute the guess solution for the function when applying the inductive hypothesis to smaller values, hence the name substitution method. This method is powerful, but we must be able to guess the form of the answer in order to apply it. We can use the substitution method to establish either upper or lower bounds on a recurrence. As an example, let us determine an upper bound on the recurrence t of n equals 2t of the floor of n over 2 plus n, which is similar to the recurrence in 4.3 and 4.4. Okay, so 4.3 and 4.4. I don't see it immediately, but that's not the most important part. So using their actual recurrence, right? Let's just take a look. So we guess that the solution is T of n equals O of log n log base or O of n log n. All right. So here we know that this thing is being broken down by twos, and then there's also this n part, right? So log base 2 of n is what we would get if we keep dividing by 2. The substitution method requires that we prove that T of n is less than or equal to C log n log n for an appropriate choice of the constant C greater than 0. We start by assuming that this bound holds for all positive m less than n. In particular, for m is n over 2, the floor of n over 2, yielding T of the floor of n over 2 less than or equal to C of, or C times the floor of n over 2 log n, floor of n over 2, substituting into the recurrence yields the following. We have 2 times C, and then notice what we have here. We just add in the n part. So as an example, let us determine an upper bound on this particular recurrence. All right, like that. So now we took this part here, okay, and this whole n log n part is in the actual equation, but the n is added in. And you'll notice that we substituted t for its algebraic equivalences. So that's why you see down here, you don't see the t of n part, you see the c part, n log n. So now if this is c of n log n, let's just take a look. By induction, it now requires us to show that our solution holds for the boundary conditions. Typically, we would do so by showing that the boundary conditions are suitable as base cases for the inductive proof. For the recurrence in 419, we must show that we can choose the constant C large enough so that the bound T of n is less than or equal to C of n log n works for the boundary conditions as well. The requirement can sometimes lead to problems. Let's assume for the sake of argument that T of 1 equals 1 is the sole boundary condition of the recurrence. Then for n equals 1, the bound T of n is less than or equal to C of n, but C times n log n yields T of 1 is less than or equal to C times 1 log of 1, which equals 0, because the log of 1, regardless of the base, will equal 0. Alternatively, you could say that any number, if we're going to get the number 1, any number raised to some other power will require that the power be 0. That way we can, have the number 1 as an outcome. So this is the odds with T of 1 equals 1. The base case of our inductive proof failed to hold, unfortunately. Now, we can improve an inductive hypothesis for a specific boundary condition with only a little more effort. It says, in the recurrence, for example, we can take advantage of asymptotic notation requiring us to only prove T of n is less than or equal to C of n log n for n greater than n0, or n naught, I should say, where n naught is a constant that we get to choose. So we keep the troublesome boundary condition of T of 1 equals 1, but remove from it consideration in the inductive proof. We do so by first observing that for n greater than 3, the recurrence does not depend directly on T of 1. Thus, we can replace T of 1 by T of 2 and T of 3 as the base cases in the inductive proof, letting n naught be equal to 2. Okay. I believe, let's see. I believe I want to stop to ask questions or to field questions, I should say. All right, who's with me still? 100%. One, two, three, four, five. All right. That was only half the class, really. Who's not quite with me? Okay, fine. Let's see.